the month. Just in advance, next month we won't have any meeting because of the holidays. And tonight is the last of our meetings in 2024. Our speaker tonight is Dominika Durovcikova. She's a fifth-year graduate student in physics at MIT, and she is working on studying of the quasars, a fascinating topic in astrophysics. Dominika has works with telescopes, ground-based as well as space-based telescopes to study these objects. And I would be delighted to hear about her experience in using the James Webb Telescope. I was a little bit involved in that very, very early on. And so I have a personal interest in that. With that introduction, I'll let Dominika, let's see, yeah, take the screen or the mouse and start the talk.
Thank you for the introduction. I requested permission to share my screen.
Okay.
Perfect. Okay, let's see. Can you see the presentation in the
I can. Can everybody see it?
Yes. Coming through.
Perfect. Thank you. So thank you very much for having me. It's my great pleasure to come here and talk to you about some of the research that I'm involved in and sort of introduce you more broadly to the topic of detecting quasars. My understanding of the audience is that people come more from the engineering side over here, and so I will spend a little bit of time at the beginning telling you about sort of some introduction to the broad topic of quasars, what they are, how far, what distances are we talking about when we talk about these quasars. I also want to sort of motivate why we generally care about detecting the light from these quasars. And one of the points I'm going to try to make is that I really want to, this light is really, really faint. And so I guess the part that's going to be of most interest to this audience perhaps is how do we detect such faint signal? And in this section, I want to talk to you a little more about the James Webb Space Telescope and sort of a little more diving into the technology and what has made it possible to really get such a good telescope operating. And then if time permits, I can conclude with the section telling you about what have we learned so far from looking at these high redshift, these distant quasars. But I would like to, make sure that everybody is on board with what I'm talking about, that I don't lose people. And so perhaps after every section, we can take questions, and we'll see if there's going to be time for the last section. Okay, so let's start with the brief introduction to the topic. So what are quasars? So I'm not sure how many of you have heard the word quasar. It's kind of, very obscure word sometimes, but we all have, in this background that I'm showing you over here, most of these or all these dots and smudges you can see are galaxies. And so the picture that we have is that, everybody has sort of seen an image of a galaxy. I can see that one participant has an image of a galaxy on their Zoom profile. So we've all sort of, see in a galaxy, as I'm showing in this picture over here. And when we talk about quasars, we usually talk about what happens sort of right in the middle of a galaxy. And in the middle of a galaxy, this is an artist's depiction of what might be happening if you zoom by quite a lot. And what you can see if you zoom in at the center of a generic galaxy is there's a supermassive black hole. And not all supermassive black holes grow actively. So black holes grow by what we call this process we call accretion, which means that they are actively consuming gas. But if there happens to be a black hole that is actively accreting at very high rates, then this is what we call a quasar. So sometimes I'm gonna use the word quasar and supermassive black hole interchangeably, but what I really mean by quasar is a black hole that is active and is actively consuming gas, actively growing. One of the questions that pops up very frequently when we talk about quasars being active black holes and observing them from very, very far away is, why do black holes actually shine, right? We're used to this notion of black holes, of this definition of a black hole where not even light can escape. But what I want to make clear right at the beginning is that when we talk about light not escaping, we're talking about the boundary that is called the event horizon. And from within that, we can't study anything because we don't have access to that light. But if we place this kind of object, this black hole, in the center of a galaxy when there's a lot of dust, a lot of gas around, a lot of plasma, there's this material that is around the black hole is as it's consumed by the black hole, it is actually the material around it in its immediate vicinity that is shining. It's not the actual black hole that's shining, but it's everything that the black hole is consuming that is emitting the radiation that we can observe. So again, showing this depiction, we have the supermassive black hole at the center of the galaxy, and we have this structure around it that we call the accretion disk, which is just, you can just imagine it as very, very hot plasma that is sort of moving around at very high speeds around the black hole because of its extreme gravitational pull. The only equation I'm going to show in this talk is this one, because I think it actually helps sort of put into perspective of what processes we're talking about here. So as I mentioned that it's the stuff around the black hole that is emitting the radiation that we can observe. And in more specific terms, it's actually that whenever I take like a mass energy or a blob of gas or a blob of plasma that is going to be consumed by this black hole, the energy in that blob is in general going to be split between some energy or some mass that is going to contribute to the growth of the black hole. So it's going to be this m dot black hole over here, which is sort of the rate at which the black hole is growing as a result of consuming this gas. But it cannot really consume material without any limit. And so there's always going to be this other part of this energy that's being consumed that's going to be radiated away. So it's almost like, when it's another way of whenever I describe my research to people, I say I study hungry black holes because these black holes want to consume gas and they're doing it at very high rates. But what's important to understand is that even though they're hungry and they're consuming a lot of gas, they cannot consume everything that's around them. And so the rest of the energy has to go somewhere. And so this radiation that's being emitted is given by this L over here, that stands for luminosity. And I want to draw your attention to this eta over here. So the symbol, which we call the radiative efficiency, this is essentially just quantifying what percentage of that energy that comes in is going to be shown away. And turns out that this radiative efficiency is on the order of like 10%. So for every single energy unit, 10% of that is going to be just radiated away into space. And for comparison, nuclear fusion, which is something that here on Earth we think about as a very energetic process, has a radiative efficiency only on the order of around 1% or even less than 1%. So this is really the most energetic process that we know of in the universe, which is why we can observe these quasars from very, very far away because they emit a ton of radiation, which, you know, is good for people like me who want to study these objects. The next thing I want to sort of introduce in this introduction is the distances that we're dealing with when I say that you can see them from far away. So I like to play this video whenever we talk about distances in astronomy, because all of us are used to, you know, Google Earth or like looking at maps, or when you fly on a plane, you can sort of see, we're used to seeing the surface of the Earth from a little far away. Now, you know, for a few people who have been fortunate enough to go to space, this is what you would see, but then the punchline here is you really have to zoom out by a great amount to even see the moon, which is what you just saw over there. And then this is the sun. So now we're at the scale of sort of the inner solar system. And then only here, you know, we're still embedded in our home galaxy in the Milky Way that you can see very nicely across the dark sky when you look up at the night sky. And then by this video, I just want to illustrate that you really, really need to zoom out very far to only leave our home galaxy. And now here we're talking about very local universe, right? So this galaxy is small compared to the vastness of space we're talking about. And, you know, at this point, we've zoomed out to a scale where every dot is not a star anymore, but every dot is a galaxy. And then we're still in the local universe. And then we have to zoom out very, very far into the past, where we might see something that I would call a high redshift quasar. So to put this more into schematic perspective, right? So I want to show this plot over here, which shows you sort of the evolution of the universe, where on the left here you have the Big Bang, and on the right here you have the present day with all the galaxies that I was just trying to show you. And the thing I don't want to dwell on this for too long, but the thing I want to draw attention to is that the time axis on the top is not linear, right? So right now we're at age of the universe around 13.8 billion years, or 14 roughly billion years. But 1 billion year is over here. And so there's actually a lot of things that happened in the first billion years. And that is sort of the, oops, I'm sorry. So this is where we are, right? And this sort of epoch around 1 billion years after the Big Bang is roughly what I'm going to be talking about when I talk about these high redshift quasars, or quasars that are very, very far away. Here I also use the word redshift, which I'm not sure if this audience is familiar with, so let me just briefly say what I mean by that, right? If I have a source that emits light, we know that the universe is expanding, and it has been expanding since the Big Bang. So if I shine this light through this expanding universe, what is going to happen is that the wavelength of the light is going to get stretched. And this is what we call a redshift. So for astronomers like me, we find redshift to be a very useful measure of both time and distance, because we know that the further something has shifted into the redder, longer wavelengths, the further away it's coming from. And so that's what's shown here on the bottom. Okay, so this is sort of the groundwork for for motivating, so we can sort of talk about these quasars. I want to pause here and ask if anyone has any questions to anything.
Yeah, Dominika, the radiation, is it isotropic or is it directional?
That is a very, very good question. So oftentimes we assume that it's isotropic just because it's really hard to study geometrical effects at such large distances. But the short answer is it depends on what radiation we're talking about. And I'm actually going to get into that in a little bit to talk a little more about the different types of radiation. But for example, you might have seen these pictures of like jets. Like you have a galaxy and then there's like jet streaming from the center. So that is usually shows up in the radio wavelengths, and that is typically not isotropic. So that's very directional, and this has been observed even in sort of the more distant universe, these like blobs that have been thrown at a very specific angle from the galaxy. But there's other types, like if something is just hot enough such that it radiates, like thermal black body radiation, then that is going to be isotropic. So really depends on the specifics.
Okay, thank you.
Any other questions for the first part? If not, okay, second part, just very briefly before I dive into the more technical things about how we actually get this light from so far away. So why do we care? So I've already shown you this picture of sort of what distances we're talking about, right? We're talking about light. If we're talking about detecting light from these quasars, we're talking about light that has been traveling towards us for 13 billion years, right? Just sort of, I like to just like sit with it for a little bit because it's really remarkable that we can achieve something like this. And so the easy way to motivate, or like one of the ways you can motivate to looking this far into the universe, looking at quasars, is because they actually help you look that far into the universe and help you study what was going on with the universe at various stages. So another sort of word that people like to use is beacons. So they serve as these beacons from very, very far away and even from intermediate distances, and you can use them to figure out how the universe has evolved. And this ultimately, comes down to some form of desire to understand where we came from and how our picture of our home galaxy and our solar system and the Earth and everything, how that is embedded in this larger context of the evolution of the whole universe. And here in this picture, this is the same picture I showed you earlier, but I tried to linearize the time axis just to drive the point home that we're really looking to the beginning of the universe. So you can see that this first billion years is very squished in there. The other part is that, when we think about black holes, and especially when like for people who have gone through like formal physics education, you learn about this theory of general relativity, which describes your very high mass, your massive objects, your large scale objects. And then you learn about something like quantum physics, which is the very small, the very uncertain, the very probabilistic world. And black holes are sort of this mysterious object where these two worlds kind of come together. And so in some ways, looking at studying black holes in different extreme studying black holes that are extreme in different ways is ultimately linked to this like desire to understand really this emblem of our of this like mystery of what's going on with the universe, where these two worlds collide and we are not exactly sure what's happening in the black hole, how the black hole is actually growing. And the more sort of astrophysical way to motivate it, which is what I'm showing in this picture over here, is that so the first picture is sort of starting from fundamental physics and like how black holes are something we fundamentally don't understand. But even from the observational side, we have observed these quasars that host supermassive black holes that are 1 billion times our sun, that have already somehow grown after 1 billion years of the age of the universe, even less than 1 billion years, as you can see on the time axis over here. And you can sort of employ some some simple models or like scalings based on our understanding of how these black holes grow. What I mentioned earlier, how you have this like mass energy split into the growth and the radiation. And you just, as we observe these quasars from further and further away, we come to a problem because it's getting harder and harder to explain how these black holes could have grown so massive so quickly in the universe. And so there's multiple things around black holes that are sort of mysterious and we don't fully understand. So these are sort of the two, as I see it, the two main motivations for why one might want to look deep into the early universe to look for these quasars. That was just a very brief motivation. So I'll stop again briefly, and I noticed that there's actually questions in the chat. So let me read them. Okay. Did a quasar have a real effect on the Earth? Also, what happens when a quasar die? So, depends on what you mean by a real effect on the Earth. I mean, they're so far away that there are more nearby quasars, right? There's quasars, there's supermassive black holes in more nearby galaxies that are very active, and that actually, you know, you can study in greater detail. If we're talking about any sort of, you know, real effect in terms of gravitation, then no, they're way too far. But, you know, the fact that we can detect radiation from them on Earth, this could be considered an effect. So I'm not exactly sure what you're asking there. And what happens when a quasars die. So a quasar, as I said, right, you have this black hole that is consuming gas, and only then it's a quasar. It shows up, it's emitting this large amount of radiation. But sometimes when that reservoir of material that it consumes is halted, so if it doesn't have anything left to consume, then the black hole would just not accrete anymore. It would not consume anything, and so you would stop seeing a lot of this radiation. But then that doesn't mean that it cannot become active again. And in fact, we think that this is what's generally happening, is that there are these periods of consuming material. Oh, and I just noticed that someone else responded to those questions. So beautiful. Thank you. Are there any more questions before we move on to the telescopes and the detectors? If not, I will go. So this is coming back to your earlier question about whether radiation is isotropic. Here I wanna, you know, when we talk about detecting these quasars and detecting the light from them, we need to be very specific about what light we're talking about and what that light can actually tell us about these objects. So here I'm just showing this, what we call an SED. This is a spectral energy distribution of a generic quasar, of a generic active black hole. And you can see it goes on the, so this is the frequency axis. And so it goes from the lowest frequencies or the longest wavelengths on the left. So from radio all the way to gamma rays, which are the shortest, most energetic, shortest, highest frequency wavelength. And so, for example, right, you can see that there are these, you know, a quasar might or might not have this jet, that I was mentioning before. So you could have more radio emission or less radio emission, which would be which would not be isotropic in general, because we think that it's really like a lot of energy sort of directed in a specific way with a certain opening angle. But then if you go to more energetic or to shorter wavelength radiation, so say the near infrared or the optical UV, you start seeing other things. So for example, this is going to be relevant for what I'm going to be talking about a little later. So this blue line is coming from the accretion disk. Remember, I showed you the accretion disk, or this artist's depiction of the accretion disk around the black hole earlier. And what I told you is that there is the structure around the quasar, which has a lot of plasma and is immediately in the vicinity of the black hole and is being actively consumed by the black hole. And so, for example, this radiation, we think that the primary mechanism for this emission is actually thermal emission, because as the black hole creates a very strong gravitational pull, so the plasma is moving very fast, and viscous forces heat up the plasma to a very high temperature, and then this temperature emits radiation just as thermally. And it turns out that for these masses of supermassive black holes, you would expect this thermal radiation from the innermost accretion disk to be in the UV. And then as you go further away from the black hole in the accretion disk, you get to the optical, to the less energetic side of radiation. And so, for example, because this is thermal, you would expect this to be pretty much isotropic. Now, the complicated story is that, of course, there's a lot more going on around a black hole that's embedded right in the center of a galaxy. So here I just want to flash the schematic. This is what people call the unified model, or it's like sort of the baseline model that people try to explain the different types of radiation. This, just to sort of follow up on the earlier question, this accretion disk, which is right in the middle over here, if you can see my cursor, is also tends to be embedded in this larger structure, which is this obscuring torus. So this is just dust that's a little further away from the black hole, and is actually what you see in this red. So this shows up usually in the near infrared. And the thermal radiation from the accretion disk should be isotropic, but there's all kinds of, there could be obscuring material, and so if you look at it from very far, you might actually not see isotropic radiation, because there could be dust, for example, or other clouds blocking that radiation. And this is actually also useful to sort of try to figure out something about how long these quasars have been accreting, or I can go into detail more, but don't want to spend too much time on it. But yeah, so I think the punchline here is that quasars actually emit radiation across the whole electromagnetic spectrum in general. Now, talking about actually detecting this light, I like to bring up this schematic, which I think very nicely illustrates what you can and what you cannot observe from the Earth. And here, sorry for the confusion, but the wavelength axis is flipped, and so you have the shortest wavelengths on the left-hand side. So the gamma rays, the most energetic radiation, is on the left-hand side of this plot, and then the radio, the least energetic, the longest wavelength radiation, is over here on the right-hand side. So, I mean, I could be talking about this plot forever, because there's different reasons why different wavelengths don't penetrate the atmosphere, or why it makes it it's impossible to observe them from the ground. But the one sort of band that's going to be most relevant for this is this band in the infrared, which is actually the band that's being targeted by the James Webb Space Telescope. And so I'd like to spend sort of the rest, or most of the rest of the talk, telling you about why infrared, how do you detect such faint light in the infrared, and what specifically James Webb Space Telescope is using to enable the sensitivity that then enables the science that people like me are doing with it. So the reason, just to make this clear right at the beginning, so the reason why for the infrared you have to go to space is because of the atmosphere. So the atmosphere contains a lot of water. And it turns out that water has vibrational and rotational frequencies at which the water molecule can vibrate that have resonances in the infrared band. And so what happens if you're an observer, and if you observe, for example, from the Earth, and you start looking at longer and longer wavelengths, the sky is just getting brighter and brighter and brighter. And so at some point you come to a point where you're trying to study a very, very faint light from very far away, but you have this blanket right here on Earth that's preventing you from looking further because it's radiating so much compared to the very faint sources that are very far away. So that's a simple reason why you really have to go to space to see anything in the near infrared. The one picture I also like to bring up in this whenever introducing James Webb Space Telescope is to just appreciate the sheer scale of things. So this is an image from NASA before. So this is still in the clean room. You can see people for scale. So this thing is really, really gigantic. And I think it's marvelous that it survived the whole trip into space, and that it's working remarkably well, producing really, really great data. Before going more into the James Webb Space Telescope, I also want to say that precisely because quasars emit radiation across the whole electromagnetic spectrum, James Webb Space Telescope is not sort of an ultimate tool to solve everything, right? Because we're looking at a very specific window. And so we ultimately also need other telescopes. And so, for example, in the optical, if you're going to study the optical emission, you can use telescopes that are here on Earth, like the Magellan telescopes, or so most of these are in the desert in Chile or in Hawaii. You can also use, of course, people are familiar with Hubble or other space telescopes that, for example, Chandra is studying the X-ray emission, or you get these radio telescopes, these antenna dishes that study the radio emission that are located in radio quiet zones around the Earth too. So just to say that James Webb Space Telescope is amazing, but it's not going to tell us everything about quasars. Okay, so let's dive more into the technical details here. So James Webb Space Telescope, as I showed you, right, the wavelength range is near infrared and mid infrared, right? So we're talking somewhere between 1 micron to 30 microns is sort of the band that James Webb Space Telescope is looking at. It's hosting 4 instruments on board. So you have all the things that start with near are the things that are looking at the near infrared band. So this is somewhere between 1 micron and 5 microns. This is near spec, near cam, nearest, because Penny just talking about each of them. Then there's this instrument MIRI, which is the only instrument aboard the James Webb Space Telescope that is actually looking at these even longer wavelengths, so between 5 microns and around 30 microns. This is going to become, this distinction between the near infrared and mid infrared is going to become important when we talk about how the telescope achieves the sensitivity that it has. Just to put things into perspective that is not a schematic, I pulled up these pictures that just show you the detectors. So I should say each of these instruments, what I mean by an instrument, right, is like you imagine you have the telescope that has the mirror that collects light, but then the light can be directed into 4 different instruments. And each of those instruments also has different observing modes. So you can take a spectrum, or you can image with them. You can do all kinds of things. But ultimately, each of them also has its own like detector or its own like chip array that is using for the actual readout of the light. And so here I'm just showing, so this is, a person holding the MIRI detector, just so you can imagine the scale of this window over here. And then this is, for example, also an image of the NIRCam detectors here. So you can see the 4 quadrants, and it's a similar size scale as the MIRI detector. Right, so you have this gigantic structure, and then you have these fairly small detectors that are doing all the magic. So let's talk more about the detectors. So the detectors are essentially, each of them essentially is this layered semiconductor detector, which allows you to translate the incoming light into a current or into a sort of charge. And you can see that there's this upper semiconductor absorber layer, which is actually different between the near infrared and the mid infrared detectors, just because different materials respond differently to different wavelengths. And when we talk about the kicking electrons and semiconductors into the valence band, we need different materials to be able to do that in the 2 different bands. Then you have this connector, and then you have this readout. Now, this readout system, I don't know too many technical details about it, but the thing that's very useful for an astronomer is that you can actually do non-destructive readout of the signal, right? So what usually happens in when you use a CCD is that you have light that is converted into a charge, and the charge is deposited. And if when you read it out, you discharge the accumulated charge. And so in this way, every time you read out, you reset the detector essentially for a CCD. For this type of detector, what is really useful is that you can actually, because instead of sort of pulling all the charge from the detector, you actually have capacitors in this readout circuit, and the capacitors allow you to, connected with a specific kind of amplifier, they allow you to actually monitor how much charge is being accumulated at various points without actually taking the charge away. Now, from an astrophysics point of view, this is super useful, because when you work with real data, what you actually get are these what people call ramps. So you get a readout, so you get this amount of signal at this time, this amount of signal at this time. And usually when you take exposures with these detectors, what happens is that you actually accumulate the charge for a little bit, and then you reset. So you discharge the capacitor, and then you start accumulating it again. Now, the reason this is really important for the work we're doing, and especially when you're talking about faint signals, is that you could, for example, have a cosmic ray hit your detector. Cosmic rays are these very high energy charged particles that are streaming through the universe. And when a cosmic ray hits your detector, which you can't really shield that well against cosmic rays, you would notice a jump, right? So you would see this ramp going up and up and up, and then you would see a jump. And that pollutes your signal, but because you have access to this whole ramp of readouts before you discharge your capacitors, you can actually reject these cosmic rays and still preserve the signal that you're observing. So this is the point here, is it's really, really useful to have this non-destructive readout when something. The other use case is, for example, if you saturate. So if you're observing something and your detector would saturate, in post-processing, you could still take the part of the ramp that is non-saturated to actually determine your signal. So all of these, all of these engineering decisions really influence the science that we're doing. So I wanted to highlight that. Now we're going to the sort of, sensitivity, right? Because you can have a detector that is capable of, is sensitive to the wavelengths that you need it to be, is able to convert that light into a charge or into some sort of current. But then we need to talk about what other things could be exciting your detector. And so in other ways, what are the noises the dominant noises that limit the level at which you can detect an astrophysical signal. Because we're in the infrared for JWST, problem number one is thermal noise, right? So I mentioned blackbody already a few times here. Blackbody spectrum is anything that has a temperature is radiating with blackbody radiation, or maybe not blackbody, but ish. So for example, here you can see that 300 Kelvin is roughly order of magnitude room temperature. And that peaks right around 10 microns. Now, I told you that the band for JWST is actually between 1 micron and roughly 30 microns. And so you can see that there's a whole range of temperatures that are, you know, sort of on the room temperature scale, or even if you cool down a little bit, they're still going to be radiating. So all the readout systems, all the mirrors, everything is going to be radiating this radiation, which is going to pollute your signal. This is also, by the way, how thermal cameras work, where because we are radiating at longer wavelengths that your eyes can see, because you can see the visible light band here, because we're at a certain temperature, we radiate in the infrared. And so that's what a typical thermal camera is looking at. So it's like operating these detectors at JWST is basically like having a thermal camera on the telescope. And so anything that gives you thermal noise is going to pollute the detector. So solution number one is what they call a passive cooling system, right? So if I know that if my detector is going to be at room temperature, it's going to it's going to emit thermal radiation that is going to mask our signal. You need to cool it down, right? And so there's this passive cooling system, which, just to put the schematic here, is actually this heat shield, right? So this is the mirror. This is the heat shield. Now the James Webb Space Telescope is in space, and it's always rotated such that the heat shield is in between sun and the mirror, as you can see in this schematic over here. And so, you know, when you're in space, you're basically in vacuum, but you still, if you were just to expose your telescope to solar radiation at that distance, you could still reach up to 85 Celsius. But at this stage, you know, that would be bad for your detector. And so the sun shield essentially helps dissipate that heat and protect the mirror and all the instruments and their electronics from solar radiation. So you can see that this helps it cool down to minus 233 Celsius, which is roughly 50 Kelvin, I think. Yeah, something like that. And it turns out that this is actually sufficient for the near infrared instruments, right? Because if I go back to the blackbody spectrum curve, the near infrared instruments operate between roughly 1 micron to 5 microns. And so if you cool down below, I don't know, 200 Kelvin, you're fine. The problem is that there's this one instrument, MIRI, which is looking at the band that is actually from roughly 5 microns to roughly 30 microns. And so there you actually have to go even a step further. And the problem, so you have to go a step further. Because, so one thing is, right, that the readout electronics have a blackbody spectrum. But then when you go to those temperatures, actually MIRI has a different problem, which is also a thermal problem, but it's coming from actually dark current noise. And so this is just a video from YouTube I took to illustrate what dark current is. So when we talk about dark current, we're talking about in the, you know, all the electrons, all the electrons in the conductors in the readout system have some random motion, right? We have this picture of like a conductor being like a train of electrons moving in one way. But in reality, what happens is that they're sort of drifting in one direction, but there's a lot of random motion of these electrons as they drift in some direction. And this random motion, the level to which they're undergoing this random motion is dependent on the temperature. And so it's like Brownian motion, right? So if you cool them down, you can allow them to move less quickly. And it turns out that for MIRI, when you cool down below a certain temperature, this is going to become the dominant source of noise, that you have all these electrons in your detector that are moving around a little too fast, generating too much noise for your mid-infrared detector to actually generate a good image. And so this video is illustrating how, I like this last part, as it's sort of quote unquote freezes or slows down the electrons, you get a sharper, more sensitive image of an astrophysical object in the mid-infrared. Now, turns out that there had to be quite a lot of engineering done on this front because the sun shield is not sufficient. And so what actually happened is that the engineers came up with this active cooling system, which is fairly complicated, but let me just give you a sort of brief outline of it. So again, we have the schematic of the telescope here, right? This over here on the left-hand side picture is this mirror. You have the sun shield over here. And then all the instruments are sort of sitting, behind the mirror. So you can't see them in the schematic on the right-hand side. And this is where all the detectors, all the instruments are, right? So this is what you need to cool. And especially the mirror, you need to cool down, turns out, to 6 Kelvin, which is basically near absolute zero. And so this cooling system is essentially, it has multiple parts, but it's one of the sort of main threats or like main ideas for how it works is it uses liquid helium, and it's using sort of the properties of like what happens when you compress and expand gas, and how the expansion of gas leads to cooling. It's more complicated than that, and I know only a little bit, but I can dive into it a little more if you're interested in that, but don't want to dwell for too long on it. But again, the point being that there's a lot going into actually achieving the sensitivity that we can have especially with MIRI, because the sun shield is not enough, and so you have to, there's a complicated system for how you extract even more heat from the detectors of MIRI that you saw in the picture earlier. So the last thing I want to mention in this section is that this is all about what I've talked to you about so far, is what happens at the stage of how you collect light and how you turn the light into a current, into something that you can work with later on as your data. But there's another big step that has to happen between when the data is collected and when the data is science ready. So when you can actually use it to do some of your science. And to illustrate, I'm gonna excuse me, I'm gonna show this data that we recently got from the James Webb Space Telescope, which at the center is showing a quasar. So this excuse me, this bright blob in the center of the picture is a quasar at redshift roughly 6, which again is one of these quasars where this light has been traveling towards us for 13 billion years. And then you can see these smudges over here. Now, it turns out that, when I just opened the data, I saw these and it's like, okay, these don't look real. So these actually come from, turns out these are actually artifacts of the instrument. And so the whole step that needs to be taken between you taking the data and the data being science ready is you need to take care of all these instrumental artifacts that by this point are fairly well understood. And so, for example, let me just illustrate this on this data, right? I showed you this before. So this data was actually taken with the NIRSPEC instrument. And it's taken with an instrument that actually sits somewhere over here. And so these four squares are the detector plane, right? These are your detectors. And then, as I said, right, with each instrument, you can take an image or you can take a spectrum. There's like different modes, excuse me, that you can employ. And all of them in some way project onto the same plane of detectors. Now, it turns out that for this specific instrument, for example, there's two modes that you can use. So there's this IFU mode, which is what I used for this data. And then there's another mode where this is MSA, this is called a microshutter array, which is sitting in a sort of different plane, you know, in front of the detectors in a different part of the plane, and has all these microshutters that you can open and close to take spectra of different objects in your field, right? So if you, for example, were to look at the background of my slide, you could open a shutter here, you can open a shutter here, you can open a shutter here, and when you take the data, you can get a nice spectrum of multiple objects at the same time. But what happens if you use a different mode on this instrument, it turns out that some of those shutters could fail to close. And so you get some light from a different object in the sort of field where you're looking with the telescope. You get that light sort of leaking in and polluting your data. And so that's essentially what's showing up over here. And so just to illustrate, so this is what you want to get out after you understand all the instrumental effects. So after you go from the business of how do I even detect a photon? How do I even detect light at this wavelength? How do I cool the telescope down to get sufficient sensitivity? Even after you have a sufficient sensitivity, you need to understand the instruments and how they interact and crosstalk in some way to really get your data science ready and to be able to learn something cool. So this is sort of the end of the third section. And we're almost at the hour, so I'm gonna pause here, ask if we have any questions. And
Yeah, excuse me, Dominika. I know these infrared detectors have a noise in them called very low frequency or 1/f noise.
yeah,
Has that
yeah,
been talked about in practice?
yes, absolutely. So, sorry. Let me go back, maybe over here. Fine. Yeah, so this 1/f noise is essentially, I mean, a generic term for a correlated noise in the data, right? And so, for example, in this like near spec IFU mode that I'm showing the data for, this was a big problem at the beginning when before people figured out how to get rid of it. And what they found out was that if you look at the way the detector is being read out, right? So you have this, actually no, let me go back to this picture. So the square here is your detector array. It has many pixels on it. And there's a different patterns you can read out in. So usually what happens is you, for example, you like read out the capacitor over here, and then you move on, read out the capacitor over here, move on, read out the capacitor over here, and then you sort of do the sweep to get your data point, and then you do it all over again. And so what I want to say is like the exact time at which this pixel over here is being read out is slightly different than the time that this pixel over here is being read out. And so what people found out is that when you just looked at the raw data, there would be these stripes of noise coming from the fact that you're just probing this correlated noise at slightly different points in time across the different array. And the way people realized to get rid of it is that in the detectors, I think there's actually some pixels around the edges that are not used for science, but are used for some form of, I don't know if calibration or something to have to do with the readout. And they realized that they can actually use the signal from those readout pixels that are not subjected to the sky or to the astrophysical signal to monitor the 1/f noise and then subtract it away from data. Not sure if that description makes sense without any images, but short answer, yes. But it seems to be a solved problem, at least for this mode. Yeah, there's another question from Shahin.
Text in the chat, in the chat box. In the chat box.
Oh, chat box, sorry. Let me. What is the most destructive thing in the universe? Again, depends on what kind of destruction you're talking about. So, I mean, black holes are pretty destructive in the example. You can find black holes that are smaller than the black holes I talked to you about. You can find them in a system where there is a star orbiting this black hole. And it's a really fascinating class of objects in the universe too, where you have this sort of star that is actually also creating this accretion disk structure around it. And sometimes what can happen is if the pull of the black hole is too powerful, it can rip the star apart. Just because the pull on one surface on one side of the star and the other side of the star, the difference between those poles is larger than the gravity that holds the star together. So you could call that a destructive.
Yeah, I have a question. I'm not sure if you have any insight into this, but for example, in these so-called night vision scopes, there's a device that's called a microchannel plate amplifier, and where the photons are actually amplified in a sort of electron cascade in these microchannel plate amplifiers. And I'm just curious if any of these devices have been used in astronomical observations for very faint light detection. And I'm just curious if you might have an insight as to why they either have or have not been used in some of these telescopes.
Thanks for the question. So I have to say I don't know specifically about these the amplifiers you mentioned. The one thing I do know about amplifiers that are used in these detectors is actually the feature of them that enables the non-destructive readout is that they're high impedance. And so when they're hooked up onto the capacitor, just the high impedance of the amplifier makes it enables the capacitor not to discharge or not to discharge too much to be able to sort of do this ramp. But unfortunately, I don't know specifics about the amplifiers you mentioned or whether they're used in the.
Well, they operate basically. Are you familiar with, for example, photoelectric
Yeah.
tubes?
Yes.
Sort of the secondary emission from light hitting a metal surface and then electrons being.
Yes.
Okay. Well, these devices work more or less on that principle. What it is, it's a series of capillary tubes that are bundled together, and they're coated on the inside with a metallic coating. So when the photons enter one end of the sort of capillary, they initially start ejecting electrons from that metallized layer inside the capillary, and then these electrons then bounce around through a differential voltage across the capillary, and as these electrons then bounce off the inner walls, they multiply the electrons that are being generated from that initial photon. So that's basically how it works. And so it's an
So it's
array of
like a shower. It's like an electron shower that you.
exactly right, and so they're being amplified by the differential voltage across the length
Mhm.
of these bundled capillaries. So the bundled capillaries then can form the image. So that's basically how these night vision devices work, by amplifying the ambient light and then converting that to the electrons, which can then be detected either on a phosphorus layer or usually as the screen simply. But I'm just curious if obviously if you don't have any insight, but I'm just curious why perhaps these devices have not been used to amplify very faint light signals in astronomical observations. There might be too noisy or not give a linear enough
Yeah,
signal.
I'm trying to think about what could be different when you're trying to use that kind of technology in space versus in these cameras. I wonder if it ultimately comes down to the noise, because right, the amplification itself must add some form of noise, because there's probably some uncertainty in terms of how many electrons you generate ultimately down the line as you shower, right? And so I wonder if you go down to really, really faint signals, then whether that stochasticity, which ultimately converts to noise, becomes important. But I'm just hypothesizing. I'm not. Yeah.
Sure. Well, I think you're probably right, because if you see any of these videos, for example, of where these night vision devices are being used, you do see a lot of these little speckles that just kind of sparkle all through the image. So
Mhm.
I imagine that that's just random noise. But anyway, I was just curious if you had any
No,
insight.
that's really. Can you repeat the name of these?
Right.
Of
They're called microchannel plate MCP amplifiers, and that's because
I'll
they're
write it.
microchannel plate, and that's because the essentially these the channels are these capillaries that are bundled
Mhm.
together into into a frame that then produces the you can produce. So essentially, you can think of each one of these capillaries as being a pixel.
I see.
So you have these bundled capillaries that form kind of a pixelated direct image. So there's no readout or anything. It's all real time. Whatever each individual capillary shower of electrons exits, then that's the signal that you're detecting on a. Usually, it's just on a phosphorus screen. The phosphorus then just lights up from the electrons in a small vacuum device. But anyway, I was just curious if any of these devices could have been possibly used for that. But as you said, it's probably the noise level is probably just unacceptable. But anyway,
Yeah,
thank you
thanks. Thank you for bringing that up. I'll look into it. I'm curious. I haven't heard of these before, but it'll be interesting to find out why astronomy is not using them, or if they are.
I had one other additional question that you probably maybe covered on, but have any quasars been have any been observed through gravitational lenses?
Yes, not a very far away quasars though. So yeah, so there's these funky systems where I think this one was observed as a triply lensed quasar, I think. So it was I mean, there's multiple examples, but there's some sort of the highest redshift I think is around 4, although I might be outdated on that number. Yeah, so there are these systems where you can see like a foreground galaxy, and then you can see like a triply imaged or doubly imaged quasar. And they're really cool because if you think about it, you have a system where it's also for the other folks in the audience. So you have a system where you have a quasar, right? And then you have a galaxy, and just the warping of the space-time around the galaxy is causing that light to that otherwise wouldn't have reached your telescope, is causing to bend that light to bend towards you. And so you can see multiple images. And the cool thing is that if there's differences in light travel time between the different images, you can actually use observations of such systems to learn something about, say, the curvature of the space-time or like of the universe. So you can really probe these like large scale properties of how our universe itself is curved, which ultimately determines the fate, right? Is it gonna expand for a very long time? Is it going to contract back down? Is it completely flat? Yes. So they're very exciting systems that do exist.
And if you don't mind, I have a couple of short questions. When you were on the first section, when you were referring to the energy from when the black hole is absorbing mass, is there a fraction of that is emitted as neutrinos?
Ooh, neutrinos. I don't think so. At least we don't fully. I haven't heard of people seeing neutrinos from quasars, and I think it might have to do with, you know, how like there's all these like laws of conservation of neutrinos, right? You have ultimately you have like some sort of conversion of particles, so you have this plasma, which, you know, in astrophysics we usually think of it mostly as just as a mixture of electrons and protons and light that are sort of interacting in this medium. And I wonder, I think this partially goes back to the problem that we don't fully know what happens to the matter as it crosses the event horizon, as it falls into the black hole, because usually when you produce neutrinos, we usually talk about some sort of conversion of, say, a proton into a neutron, or so there's sort of other reactions, and I'm not exactly that we have the capability to observe traces of those reactions. So unfortunately, I don't think that people usually think about neutrinos.
I think you're right, Dominika. Radiation comes from accelerating charged particles. So you have to have electrons and protons and others who have charges, and when they accelerate, then they radiate. So if you don't have charged particle, you don't have radiation. Unless there is a breakup.
Yes. Yeah, so there's, right, I'm gonna scroll back to this picture, right? So there's different kinds of radiation, right? So for example, I mean, this dust emission you can have even without the even without the charged particle, because this is mostly, you have these dust grains and they can scatter light. Or that's sort of the one way of emission. So you just get sort of scattering, or they're just at some temperature and they radiate thermally. So you don't necessarily need to have charged particles for all the different radiation, but definitely when we think about the accretion disk and what's happening right around the black hole, we think about charged particles, and then there's also magnetic fields, and
But that light has to come from somewhere else to scatter from neutrons so that you can see that. And then depending on the velocity of the neutrons, you get different wavelengths, different bandwidth from scattered radiation. I had a question on this same chart. How do you know, for instance, you look at the green curve, how do you know that's a reflection?
So this comes, so the knowledge of the X-ray part, or the high energy part of the spectrum, mostly comes from nearby. What I call nearby is something that's not 13 billion years away, but like nearby quasars. And what people have observed is that if you not just take spectrum, but you keep taking spectra at various times, so you have sort of a video of spectral information for your quasar, what people have actually found out is that there are these echoes that sometimes reverberate through the spectrum, which, so for example, right, people would, for example, observe a variation over here that would then show up in the same way in a different part of the spectrum. And if I pull up this image, so people have, for example, interpreted this as like you have light originating from say the accretion, or say the what people call the corona is just a generic term for like where the part that emits X-rays. And what people have observed is that if you have some variability in the X-ray, so if the spectral features do something, then that light can get scattered off of the accretion disk, for example, and show up in, say, the UV in the same variation. So this is just one example of like one part of light scattering from another part of the system. Now this reflection part, so you can see this corona I was talking to you about is like, is the cyan line. What people call reflection is I don't fully, I think this is just a schematic. This is just one type that you could see. I don't fully know why the author of this figure decided to put it over here, but there could be things you can call reflection also in the optical, in the UV. It's just light sort of from one structure around the black hole scattering from different parts. And that's coming back to the observations where people have seen sort of something spike up in the X-ray and then show up a little later, which is actually another cool feature because then you can actually use the light travel time. So the delay between those variabilities in different parts of the spectrum you can use the delay as the light travel time between the different structures that correspond to the different emission mechanisms. And people have used this to determine the spatial extent of, for example, the accretion disk, or the spatial extent of this dusty structure. So it's like the light bouncing around the different parts of the active of the environment of the active black hole can be used to map out spatially where things are, which is unfortunately not possible for high redshift when you look at very far away, or people have not done it yet. But
I had one, and I promise my last question.
Go
You
ahead,
were
please.
mentioning when you mentioned the accretion model for the growth of the quasars, and I understand that there might be a second growth mechanism, which is that of merger of several, or at least two
Yeah,
supermassive black holes.
correct. Yeah.
And so, are you familiar with the nanograph results, which were released not too long ago? The nanograph studies,
Yeah. Yes.
the pulsar timing studies. And so, I was just wondering,
Yes.
has any observed quasar been determined to perhaps have resulted from a merger and not just a accretion? And that'll just be my last question. Thank you.
This is exactly sort of going in the direction of or the question that my research is sort of tackling, which is, answering this question of how do these quasars grow? How do these black holes grow so fast? I'm gonna just flip back quickly into this picture I was showing here, right? So what you're saying very correctly is that instead of having this like continuous accretion and consumption of gas that will lead to the growth of the black hole, you could have a merger. So you would have two black holes sort of merging together, or not even two black holes merging together, but having, say, two galaxies collide, and that just fueling much more gas onto the black hole that would otherwise be possible. You would get these jumps in this curve, which could allow a faster growth. So what's cool is that I'm gonna flip to the last section that I don't have time to go into, but I can just flip to this picture, which is so one of the things that the JWST has allowed us to do is to take a pretty close look at the galaxies where these quasars reside. And one very, I would say, pretty surprising result that has only actually this year been sort of published and more established is that when you take a look at the host galaxies of these black holes, they seem to actually not be your classical galaxy that I showed you at the beginning, that is just like, you know, a single galaxy with some spiral arms and whatever, and then you have a black hole in the middle. But it seems to be a more complicated morphology with all these blobs that seem to indicate that there's actually active mergers going on. So, for example, here, there's two examples of these quasars. So, for example, this one on the left is a clearer one, where this cross marks the location of the quasar. So it's this like point source light, intense light that you see in your data. And then what you do is you model and subtract that light, and that allows you to see this fainter structure underneath, which is your host galaxy. And this is just showing you that there's obviously some galaxy that's hosting the quasar, but there's this blob over here, which seems to be morphologically distinct and could be another galaxy sort of falling in. And there also seems to be a third blob, which is sort of following the trail. So this could even be like a trail of galaxies that we see actively, maybe even fueling the quasar, or this is another example of that, where you can, again, this cross is marking the location of the quasar that has been subtracted away from the data. And you can see, again, not just a single nice host galaxy, but you can see another blob over here. And even if this was already one galaxy, the fact that it has this really weird morphology indicates that it could have undergone a merger recently. So this is a very, very active area of study, and this is just one example of results that have indicated that indeed the growth history of these black holes is not as simple as just continuous consumption. Oh, I can see another question in the chat. LIGO is being used to observe a quasar. It's for gravitational. Oh, so let me make a distinction between gravitational lensing and LIGO. So gravitational lensing is this structure where you have a massive object bending space-time such that you can see what's behind it. LIGO is a gravitational wave observatory. And so what that means is that, for example, if we have two black holes orbiting each other, they send these ripples into space-time that propagate, and that can be detected by LIGO. As for quasars, it turns out single object, single black hole cannot really emit gravitational waves. So LIGO is not really relevant for quasars. Since we're talked about mergers, if you have two, you can imagine a scenario where you have two supermassive black holes, orbiting each other or undergoing a merger. Turns out that could send ripples through space-time, but is in a very different frequency range than what LIGO here on Earth is sensitive to. But maybe you've heard of this project called LISA, which is the space observatory for gravitational waves that is being developed and is being worked on, which is one of the goals is to actually observe systems like this. So stay tuned. Okay, do we have any more questions? I think at this point we skipped the last part, but I'm happy to take some more questions to make sure people are happy. And in the meantime, maybe I'll actually flip to the summary slide so you can sort of summarize what we've talked about so far. In the first part, I tried to introduce you briefly to the topic, and the point of that section is really just that quasars are these actively accreting supermassive black holes that emit a lot of light, and so it can be seen from very far away. The second section is this, why do we care about detecting this light? Why would one want to build a huge telescope to detect this light? Mostly to study the universe, how the universe evolved, and how to understand the most mysterious objects in it, so these black holes. And then I told you about how we detect the signal, and that the space telescope, which is paired with an exquisite sensitivity with this detector technology we talked about, and also thanks to all the cooling systems, is really crucial to detect the signal.
Okay. Any other questions? If not, let's thank our speaker for a very fascinating talk.
Thank you so much for attention and for all the questions.
Sure, and I also want to thank Lubos for introducing Dominika to our chapter, and he's the one who started this whole issue with us. And I'm grateful that Dominika could accommodate us. I know it's late night for her, but hopefully we will hear from her again. And thank you.
Thank you so much.
Thanks everybody for attending and asking questions. I guess this is the end of our meeting tonight, and I'm going to say goodbye.